Good evening, dear students. Today we will be discussing probability. This is in continuation of whatever we have discussed in the last class. So the last class video lecture is available in the online test platform at KonarClasses.com, as well as it is available in YouTube. You can always refer to that one. Now today we will start with the set theoretic principle of probability. Now, before I proceed, just would like to get confirmation from a couple of students that you are able to hear my voice very clearly and able to view the screen properly, dear students.
Yes, sir.
Okay, thank you very much for your
Yes, sir.
confirmation. Okay, all right, thanks. Couple of confirmation is sufficient. So, dear students, we will discuss the set theoretic principles of probability. So here, with respect to the sample space S, okay, we take two events A and B, and we view these two events as like sets. Okay, so what does it mean? Suppose you our event is that while throwing a die, which is a random experiment, getting an even phase. Okay, so if you see this, the entire sample space. Okay, entire sample space has 1, 2, 3, 4, 5, 6, right? That is the entire sample space. Now we have here, the event A. We define the event A as getting an even phase. Then what are the values you should get here? The values you should get here is that 2, 4, and 6. Correct? So then 2, 4, 6 is like a set. And then not getting an even phase, that means getting an odd phase, it is 1, 3, 5. So then, dear students, if you see the entire set S is actually 1, 2, 3, 4, 5, 6. And the set A, that is actually the set A is nothing but the representation of the event A. So what is our event A? Event A is that getting an even phase. So it says either 2 or 4 or 6 from the sample space set S. And similarly, we can get the set B, which is complement to A with respect to the sample space S. That means getting an odd phase, and it represents the set containing 3 elements, 1, 3, and 5. So dear students, with this example, that I just wanted to tell you that how you can represent an event in a set theoretic manner. So keeping this in mind, so I would like to tell you these points, and followed by I will explain. And here it is, dear students, is that let A and B be two events in a sample space S. Okay, like this, the event what I just explained you a minute back. Let A and B be two events in a sample space A. Then A union B means occurrence of at least one of A or of B. A intersection B means simultaneous occurrence of both the events A and B. A bar or A prime or A complement, A power C, that is C is there in the subscript of A, means that non-occurrence of A. Now if you see A bar intersection B bar, or A prime intersection B prime, or A complement intersection B complement, all represent the same thing, means that non-occurrence of both A and B. Okay, A is an improper subset of B, means occurrence of B is implying that occurrence of A. So if you see, dear students, in all these 5 cases, what I I just showed you is that you see it is a set theoretic operations here: union, intersection, complement. Okay, and what is the exact meaning of it that I explained? For example, A union B. You know what is A union B from a set theory, from the knowledge of your sets, but it's represent in the abstraction of probability. The meaning of A union B is that occurrence of at least A or of B. For example, in the example what I just said few minutes back, that what is our event A? Getting an even phase. What is event B? Getting an odd phase. Now, that is related to the random experiment called throwing a die. Now, what is A union B means then? A union B means is that occurrence of at least one from even number set or from odd number set. That's what is A union B means. In the similar manner, A intersection B, A complement, and A complement intersection B complement, and A is a subset of B has its own meaning in as long as the probability statement is concerned. Now, dear students, why we are learning that set theoretic principles of probability? It is going to help us to find the probability when there are two events involved or more than two events involved. For example, we have two events A and B. Okay, two events A and B in a sample space S. Now, that our set theoretic knowledge will help us to find the probability of A union B. Okay, so let us discuss all these things in details, dear students, so that it will be very clear to you. Okay, and that is related to the addition rule of probability. So what we are going to discuss now is the addition rule of probability. So dear students, if you look into it, let A and B be two events in a sample space S. Now, the probability of the event that at least one of the events A and B will occur is denoted by PA union B and is defined as PA union B is equal to PA plus PB minus P of A intersection B. Dear students, if you remember that your understanding or set theory, that how we compute the number of elements in the set A union B, that is equal to number of elements in the set A plus number of elements in the set B minus number of elements in the set A intersection B. It is actually similar to that. Here only it is a probability. By the way, all these things you see, that probability of A union B, probability of A, probability of B, probability of A intersection B, all these are values between 0 and 1, including both 0 and 1. Okay, so that is what is denoted by probability of A union B, and it is very frequently used. Now, related to this addition rule of probability, I would like to tell you the following points one by one, and I will also explain you accordingly. The first one, dear students, what I'm going to discuss is that if the event A and B are mutually exclusive event. Dear students, in the previous session we discussed in details about the mutually exclusive events. Mutually exclusive event means is that A intersection B is a null set. If A intersection B is a null set, then obviously probability of A intersection B should be 0. And in that case, what we get, dear students, is that probability of A union B is now turning out to be probability of A plus probability of B. How? Because we know that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Now, as the events A and B are mutually exclusive, then definitely that A intersection B is a null set, and probability of A intersection B is eventually 0. So in that case, what will happen is that as this is becoming 0, so what we get is that from here we can write that probability of A union B is equal to probability of A plus probability of B when events A and B are mutually exclusive events. Remember this thing, dear students. It is going to be very helpful to you. The next point what I'm going to discuss, dear students, is that probability of A complement. Probability of A complement is nothing but 1 minus probability of A. That is what is known as probability of A complement. That we all are aware. For example, if we know that if we throw a die, probability of getting an even face is 1 by 2, then what is the probability of getting odd face, which is complement to the even face, is that 1 minus probability of getting that even face, that is 1 minus 1 by 2, that is actually also 1 by 2. So this is the second one. And the next property said, dear students, what I am going to show you, it is, if you remember, that is going to be a very, very helpful to you in solving problems related to the probability, where the set theoretic notation is actually applicable. And here is, dear students, first one is that probability of A intersection B complement. Probability of A intersection B complement is equal to probability of A minus probability of A intersection B. Next one is that probability of A complement intersection B, that is equal to probability of B minus probability of A intersection B. Third point is that probability of A complement union B complement is nothing but 1 minus probability of A intersection B. Take care of that. In the left hand side it is union, but in right hand side it is intersection. I repeat, probability of A complement union B complement is equal to 1 minus probability of A intersection B. Next point, dear students, is that probability of A complement intersection B complement is equal to 1 minus probability of A union B. Probability of exactly one of A, B occurs is nothing but probability of A complement union B complement minus probability of A complement intersection B complement. And the next one is that maximum of probability of A plus probability of B minus 1, probability of A and probability of B, means in these three numbers, the probability of A plus probability of B minus 1, comma, probability of A and probability of B is always less than equal to probability of A union B less than equal to probability of A plus probability of B. That is also very important information. Now, dear students, how you can make sure all these statements what I have written is true? Obviously it is true because I am saying, and it is proven also. But the thing is that you can practically take an example. Okay, you choose your random experiment, you choose two events, and then write down their probability and experiment all these cases whatever I have just written, and you will see it is exactly matching. In case of any doubt, then you can always get back to me later. But this is the way you can exactly practically realize how these equations are actually working, equalities are working. And now let me proceed to the next point. When instead of these two sets, we are going for three sets. That means instead of two events, we are now going to the three events. And that we are going to discuss now. And if we take three events, A, B, and C. If we take A, B, and C, then the first and very important formula that you need to remember is something like this. I'm going to show you now. Very important formula, dear students, and you need to remember this thing. And it says that, dear students, is that let A, B, and C be three events in a sample space S. Let A, B, and C be three events in a sample space S. Then we get the following. The first one is probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. Dear students, if you recall, your understanding in set theory, there also, when you find the number of elements in the set A union B union C, you use this formula. Here it is, instead of number of elements, it becomes a probability. Just giving an analogy to remember things. So this is one of the most important formula when there are three sets involved. Proof of this formula, as I said, you can choose your random experiment, you choose three events, find their probability, make their intersection and union, and compute it, and you will see that these equalities are actually holding true. Generally, what happened is that you may have a question, sir, where I need to apply these formulas. You need to apply these equalities or formulas, the way you want to name it, is that when you see that from that problem statement you have enough information to a probability of A, probability of B, probability of C, or and the other information like A intersection B, B intersection C, C intersection A, and A intersection B intersection C. You have information of all these probabilities. Now from there you can find the probability of A union B union C simply by using this formula. Correct, dear students? Now, as I said a minute back, this is one of the important formula when three events are involved. Apart from that, there are three more I'm going to tell you, and remembering these three formulas, what I'm going to show you now, will help you to solve relatively complex problem in a much simpler manner. What is that? The second one is that probability of exactly one of A, B, C occurs. Probability of exactly one of A, B, C occurs, that is equal to probability of A plus probability of B plus probability of C minus 2 times probability A intersection B minus 2 times probability of B intersection C minus 2 times probability of C intersection A plus 3 times probability of A intersection B intersection C. Next one is that probability of exactly 2 of ABC occur. That is equal to probability of A intersection B plus probability of B intersection C plus probability of C intersection A minus 3 times of probability of A intersection B intersection C. Now the next one is that probability of at least 2 of ABC occur. That is equal to probability of A intersection B plus probability of B intersection C plus probability of C intersection A minus 2 times of probability of A intersection B intersection C. These are the formulas related to the three events, dear students. And if you recall, and if you similar things we discussed in the set theories, but here with respect to probability. I repeat, dear students, remembering these formulas will help you to solve the problems related to set theory probability. Whenever you need to apply the set theoretic concept, it will be very, very easy. Now, dear students, the next point what I'm going to discuss is that conditional probability, and that is a very important topic, and I'm going to discuss on conditional probability now. Okay, Let A and B be two events in a sample space S. Now, the probability of the event A subject to the condition that event B happened, that we are going to discuss. Let me give you an example. What is meant by conditional probability? Think about that we are rolling a die. Okay, what is our experiment? Our experiment is rolling a die. That is a random experiment. Now, if I ask any one of you, hey dear students, I am rolling a die, could you please tell me what is the probability of getting the phase 2? You can say, sir, it is easy. It is 1 by 6. Why? Because number of favorable events, number of cases favorable to the event is 1. That is 2 can come only 1, and divided by total number of events is 6. So the probability, you can say that probability of that event, what you can say is that probability of that event A, if we say that event A is that getting a phase 2 is equal to 1 by 6. Now I change the problem little bit. I'm telling you, that dear students, that I roll a die and I got an even phase. That I'm informing you that I roll a die and I got an even phase. Now can you please tell me what is the probability of getting a phase 2? At that time you will tell, oh sir, it is 1 by 3. Why? Because you already told me that you got an even phase. That means my sample space reduces to 2, 4 and 6. What was the original sample space? Original sample space was 1, 2, 3, 4, 5, 6. And from there, it actually shrink up to, dear students, it becomes 2, 4 and 6. Why? Because I am informing you upfront that, hey, dear students, I roll a die and I got an even phase. So the moment you hear that statement that I got an even phase, then the sample space reduces to 2, 4, 6. Now if I ask you a question, dear students, hey, what is the probability that I get a phase 2? Okay, in that case, suppose I called it as an event B, then you say, oh sir, it will be 1 by 3. Why? Because out of 2, 4, 6, 2 can happen 1. So number of cases favorable to the event is 1 and total number of cases is 3. So 1 by 3. You see, dear students, when I was asking that I roll a die and what is the probability that I get a phase 2? Your answer was 1 by 6. And then I say, hey, I roll a die and I got an even phase. Then you tell me what is the probability of getting a phase 2. You say it is 1 by 3. In the second case, that is called as conditional probability. Why? Because I imposed a condition. And what was the condition? That I got an even phase. That means I got either 2 or 4 or 6. And that is what is called conditional probability. So as I give you the example, dear students, now let me come to the formal definition of conditional probability. Okay, so let me first take the statement from the study material. Let me place it here, and after that we'll start discussing on it. So what is that? Let A and B be two events. Let A and B be two events in a sample space S. Now, the probability, precisely known as conditional probability of the event A, subject to the condition that the event B has happened, is denoted by probability of A bar A slash B, and it is defined as probability of A intersection B divided by probability of B subject to the condition that probability of B is not equal to 0. If probability is B is equal to 0, then there is no point of discussing further in conditional probability, because our discussion on conditional probability under the assumption that B has happened. Now, if probability of B is equal to 0, then, B has happened with, no, B actually doesn't happen, or, set theoretic representation of B is a null set. Correct. So that's why probability of B is 0. So we should not discuss about probability of B is equal to 0. So probability of A, slash B, we define like this. So I can write it here, dear students, that probability of A, okay, subject to the condition B has happened. Sometimes, oblique also people write that probability of A subject to the condition B has happened. For example, in case of our example, that we roll a die and we got a even phase. So what is the event B? So let me write it down, the definition first. It is probability of A intersection B divided by probability of B. Now, in our case, when the moment I say, hey, I roll a die and I got an even phase, so B is the event, got an even phase. So what is the probability of B? Probability of B is that when you roll a die, you can either get an even phase or get an odd phase, right? So it is actually probability of B is 1/2. Now, what is A? A is actually, getting the phase 2. So its set theoretic representation is 2. And what is the event B? Event B is that you get an even phase. That means 2, 4, 6. And what is then A intersection B? From here, what you can write, dear students, that A intersection B is equal to only 2. So what you can write about that probability of A intersection B is equal to 1/6 divided by probability of B is that 1/2. That is equal to what? 2/6, which is nothing but 1/3. Exactly 1/3 got it here. But when we discussed earlier, I just give an example without having the understanding about the formula. That probability of A slash B is equal to probability of A intersection B divided by probability of B, subject to the condition that probability of B is not equal to 0. Okay. Now, let us take an example. Okay, let us understand conditional probability by means of an example. Let a family has 2 children. Okay, let me first show you the problem, and then we'll discuss this thing. Let us understand conditional probability, okay, by means of another example. One example I already informed. Another example I'm going to discuss with you. And that is also a very interesting example. You will like it. Okay, so let us understand conditional probability by means of an example. What is that example, dear students? Let a family has 2 children. What is the probability that both the children are boys, given that at least one of them is a boy? You see, dear students, that the moment this statement is there, given that at least one of them is a boy, that actually leads you to think that, oh, it is a problem where I need to apply conditional probability concept. If the question is that what is the probability that both the children are boys, that is a completely different question. Okay, there you don't need to apply the concept of conditional probability. But the moment you get the question that what is the probability that both the children are boys, given that at least one of them is a boy, that leads to the concept of conditional probability. Let us understand this problem. So, let A be the event. So how we can define the event? So defining the, framing the event is very, very important here. Okay. So how we are going to do this thing, dear students? How we are going to approach this particular problem? Here it is. Let A be the event. Both the children are boys, and B is the event. okay, B be the event that at least one of them is a boy. So there are two events we are defining. Event A, both the children are boys, and event B, that at least one of them is a boy. Then what you need to find according to the question? We need to find that what is the probability of A slash B. That means what is the probability that both the children are boys subject to the condition that at least one of them is a boy. Correct? Exactly, it represents that probability of A slash B represent the problem statement what has been given. Now, what is the formula? The formula for probability of A intersection B, sorry, not A intersection B, slip of my tongue, probability of A slash B, that is equal to what? Probability of A intersection B divided by probability of B. So all we need to find is the probability of A intersection B and probability of B. Now, if we see the sample space, okay, the entire sample space, we can see there are four. Entire sample space is 4, and we see what? Let me show you this thing that what are the entire sample space. So the entire sample space as two children, then the entire sample space is something like this. The first one is that BB, that is both the children are boys. That is the first one. Second one is that BG, the first child is a boy and the second child is a girl. Then next one is GB, the first child is a girl and the second child is a boy. And the fourth one is GG, both the children are girls. Okay, so this is the entire sample space what we can think of. Now in that sample space, what we can find it out, dear students, is that let's find what is A. What is A? If you just think about what is A is the event both the children are boys. So our set theoretic notation, if we apply the set theoretic notation, what is the set A it's coming? It is actually coming BB, isn't it? Because it represents both the children are boys. And what is the event B? Event B is that at least one of them is a boy. So then what is the set theoretic notation of the event B? It should be BB, BG or GB. So BB, sorry, BG or GB. Correct, dear students? That actually represents at least one of them is a boy. Now, if as we see that A and B sets are there, it is very easy for us to find what is A intersection B. So A intersection B, we find BB. Correct, dear students? Now, what is probability of B? Probability of B is actually 3 by 4. How come probability of B is 3 by 4? Probability of B, if you look into it, is that B set contains 3 elements. The tuple BB, then the tuple BG, and then tuple GB. And how many total, a sample space containing how many elements? 4. So 3 by 4, that is the probability of event B. And what is the probability of, A intersection B? Probability of A intersection B is eventually 1 by 4. Why? Because the set A intersection B contains 1 element and the entire sample space contains 4 elements. So obviously, it is 1 by 4. Now the value of probability of A intersection B and probability of B, if we apply in the formula, so what we are going to get, dear students, that probability of A subject to the condition B has happened, that is probability of A slash B is equal to probability of A intersection B, that is 1 by 4 divided by 3 by 4, and that is nothing but 1 by 3. And hence we are able to answer Okay, what is the probability that both the children are boys, given that at least one of them is a boy? Correct, dear students? Got it? Now, the next very important point what we are going to discuss is called the independent events. Okay, and let me take you to the next page to discuss about independent events. And it is very important to understand independent events. After that, I'll discuss about that, uh, mutually exclusive events, and we will see, the difference between mutually exclusiveness and independence. Very important point that we'll discuss. Mutually exclusive events we are already aware of, but when you understand about independent event, sometimes students get confused that looks like mutually exclusive, but not really. Let me explain you what is independent events. Let A and B be two events in a sample space S. Now, these events, that is A and B, are said to be independent if the probability of occurrence or non-occurrence of the event A does not affect the probability of occurrence or non-occurrence of the event B, and vice versa. Okay, you may think, okay, can you give an example that will be helpful to us to understand that what is independent events and what is not independent events. Let us understand. Okay, let us take two cards. Okay, let two cards are drawn in two trials from a deck of cards. The deck of cards, it contains the 52 cards. Out of these 52 cards, two cards are drawn in two trials from a deck of cards. Now, so let me first, explain this with the example. I'm taking it from my study material. Let me first explain you, with an example, and then I will, give the proper definition, means the theoretical definition of independent events. Let us understand that independent event and that these independent events and independent event by means of example. These independent events, let us understand independent events by means of an example. Okay. Two cards are drawn in two trials from a deck of cards. Let us understand the following two events. Event A, drawing a red color on the first trial, and event B is drawing a red color on the second trial. Now, can we say that events A and B are independent to each other? Okay, let's see. Now, these two events, A and B, will be independent or dependent based on whether the card is replaced after the first trial or not. I repeat, these two events A and B will be independent or dependent based on whether the card is replaced after the first trial or not. And here it is. If the two cards are drawn with replacement from a deck of cards, then the events of drawing a red on the first trial and the drawing a red on the second trial are independent of each other. Why? Because you replaced. So as if when the event B is going to happen, it is a fresh deck of 52 cards. But if the two events are drawn without replacement from a deck of cards, then the event of drawing a red card on the first trial and that of drawing a red in the second trial are not independent, because their occurrence of the red in the second trial is actually influenced by the occurrence of red in the first trial, that is event A. So let me first write down this statement, what I just said you, and then I'll come to the definition of independent event. Now, these two events A and B, I repeat, Now these two events, A and B, will be independent or dependent based on whether the card is replaced after the first trial or not. And following is the explanation. If the two cards are drawn with replacement from a deck of cards, the event of drawing a red card on the first trial and that of drawing a red card on the second trial are independent of each other. Why? Because first trial, when you draw a red, event A happen, after that you replace back that card into the deck of cards. Then when on the eve of happening the event B, as if it is a fresh set of 52 cards. So that probability, the occurrence of the event B has no relations with the occurrence of the event A. But in the second case, if the two cards are drawn without replacement from a deck of cards, then the event of drawing a red card on the first trial and that drawing a red card on the second trial are not independent of each other. For example, if you, first event A happens and you got a red card, then how many red cards will be left after the event A and the card is not replaced back? It will be less than 1. Correct? Correct or not? There are 26 red card and 26 not red card. So the moment the event A happens, that means in the first trial you got a red card, and that red card, what has been drawn, it's not replaced back. Then before happening the event B, how many red cards we have? It is not 26, it is 25. Then finding a red card out of those 25 is actually influenced because one red card is already taken care by the event A. They are not, in that case, they are not independent. They are in fact strongly dependent events in that case. So now, dear students, let me come to the definition of independent events, and let me after that we will proceed further. So what is that? Let A and B be two events. Let me first show you the material here, and then let me explain. Let A and B be two events in a sample space. Yes. Now these events A and B are said to be independent events if the probability of occurrence or non-occurrence of the event A does not affect the probability of occurrence or non-occurrence of the event B, and vice versa. That is, we can say the following, that probability of B/A is equal to probability of B. How? Let me explain you. What is probability of B/A means? Probability of B/A means that probability of the event B subject to the condition A has happened. Probability of B/A means probability of the event B subject to the condition A has happened. Now, if the occurrence or non-occurrence of the event B is not influenced by or not affected by the occurrence or non-occurrence of the event A, then we can directly say this is equal to probability of B, because occurrence or non-occurrence of the event B has no relation with the occurrence of event A and event B. No occurrence or non-occurrence of the event A. So now, what is probability of B/A? That is nothing but probability of B intersection A divided by probability of A. That should be equal to probability of B. Correct, dear students? Okay. So now what we can get is that, so from here what we get is that probability of B intersection A is equal to probability of B into probability of A, and we can write it in proper sequential form. Probability of A intersection B is equal to probability of A into probability of B. Okay, so this is the way we define that probability of A intersection B. So when you find the probability of A intersection B is equal to probability of A into probability of B, then you can safely conclude that A and B are independent events. Whatever I wrote in the red color, it has been properly derived here. You see, probability of B slash A is equal to probability of B when probability of A is not equal to 0, and probability of A slash B is equal to probability of A when probability of B is not equal to 0. Obviously, probability of A not equal to 0 and probability of B not equal to 0, you understood. Then what we get, probability of A intersection B by probability of A is equal to probability of B when probability of A is not equal to 0, and probability of A intersection B by probability of B is equal to probability of A when probability of B is not equal to 0. So finally what we get, probability of A intersection B is equal to probability of A into probability of B. This is the required condition to conclude whether the events A and B are independent or not. If events are not independent, then we say that the events are dependent. That means two events could be either independent to each other or dependent on each other. So if A and B are independent, then probability of A intersection B is equal to probability of A into probability of B. And if the events are not independent, then we can say they are dependent. Now, by hearing about this, that independent events, and you also have a knowledge about the mutually exclusive events, I would like to tell you that there is a difference between mutually exclusiveness and independence, and we should know this difference very well. And I am going to explain you this difference now in this next page. So what is the difference between mutually exclusiveness and independence? Dear students, mutually exclusiveness is a property of sets, whereas independence is a property of probability. That is the first difference. In fact, mutually exclusive events are not independent events, and vice versa. Okay, let us understand why I am saying so. Okay, let us understand why I am saying so. So, let me first write down the statement and then I'll explain in details. So let me read out, dear students. Mutually exclusiveness is a property of set, whereas independence is a property of probability. So mutually exclusiveness is a property of set and independence is a property of probability. In fact, mutually exclusive events are not independent and vice versa. That means is that the converse is also true. Let us understand by means of the following two cases. I want to take two cases to explain that mutually exclusive events are not independent and vice versa. How? Let us take the first case, dear students. That let us consider that A and B are mutually exclusive. Okay. So let us assume in the first case, dear students, that let me write it down here. That let A and B be two events in a sample space S such that A and B are mutually exclusive events and probability of A and probability of B are not equal to 0. Both are not equal to 0. Now, what you are going to get? A intersection B is equal to phi. Why? Because A and B are mutually exclusive events. From our knowledge of mutually exclusive events, we can say that two events A and B are mutually exclusive if A intersection B is equal to phi. The moment A intersection B is equal to phi, dear students, what we can say? That probability of A intersection B should be equal to 0. Obvious. Now, probability of A intersection B is equal to 0. That means what? Probability of A intersection B is not equal to probability of A into probability of B, because probability of A and probability of B both are not equal to 0. So obviously probability of A into probability of B is not equal to 0. But we saw that probability of A intersection B is equal to 0. That means what? probability of A intersection B is not equal to probability of A into probability of B? Now, we learned few minutes back that for independent events, probability of A intersection B has to be equal to probability of A into probability of B. But what we see here, that probability of A intersection B is not equal to probability of A into probability of B, where A and B are mutually exclusive events. So we conclude that two events mutually exclusive to each other are not independent to each other. Very important statement. Okay. So we see that two events mutually exclusive to each other are not independent to each other. Rather, they are strongly dependent. Okay. Now I'm going to take the second case, dear students. In the second case, what I'm going to take is that I'm going to take the two, let me take the second case. The two events A and B, what we are going to take, they are independent. Okay. And we'll show them that they are not mutually exclusive. Okay. Which is the vice versa part. So let me take the second case, dear students, first. So in the second case, what I'm going to take is that let A and B be two events. So let us take A and B be two events in a sample space S such that A and B are independent to each other and probability of A not equal to 0, not equal to probability of B. That is an obvious condition, dear students. Now we get the following. We assume that events A and B are independent. So we are free to write that probability of A intersection B is equal to probability of A into probability of B. Now, as probability of A is not equal to 0 and probability of B not equal to 0, that means probability of A into probability of B is not equal to 0. Eventually, it means that probability of A intersection B is not equal to 0. Now, dear students, if probability of A intersection B is not equal to 0, that means what? A intersection B, from a set theoretic notation, we can say is not a null set. Correct or not? Because if an event represents a null set, then only its probability is 0. But here we see that probability of A intersection B is not equal to 0. That means what? A intersection B is not a null set. That means A intersection B is not equal to phi. But A intersection B not equal to phi means what? They are not mutually exclusive. Because to have two events mutually exclusive, their intersection has to be a phi. But here we see what? A intersection B is not equal to phi. So what we see, that two events independent to each other, but are not mutually exclusive to each other. So dear students, there is a great difference between that mutually exclusiveness and independence. And I explain this thing, in this class today. Now, dear students, I would like to, conclude the class for today, because in the next class, we are going to discuss two important things. One is called the total probability theorem and Bayes theorem. Till that happen, dear students, in our next class, I will strongly suggest you to please visit www.KonarClasses.com and appear for. So visit www.KonarClasses.com and look for quality video lectures. Okay, appear DPPs, that is known as daily practice problems. Then after DPP, you can go for PTs, that is called practice tests. Then after PTs, you can go for UTs, that is known as unit tests. After UTs, you can go to MDTs, that is called module tests. And after MDTs, you can go to MTs, that is called mock tests. And after that, a great rank for your engineering and medical entrance is in your hand, and a great score for your board examination is ensured. So dear students, make use of this platform www.KonarClasses.com effectively. I hope all of you have login to KonarClasses.com. If someone of you do not have login, you can always be in touch with us. And here is our contact details. I'm writing it here. It is, you can call or WhatsApp in the number 80950100670, and our email is contact@KonarClasses.com. With this note, dear students, I would like to conclude the class for today. Thank you very much and see you in the next class.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.